Nested quadrature rules are the final ingredient to defining sparse grids. And what are nested quadrature rules? These are quadrature rules that if I somehow increase the order, the number of points, that then they contain the points from the previous quadrature rule that I've looked at. And now I'm going to use the term level. So in the following, we assume that we have nested quadrature rules. Oops. That means we have a sequence of quadrature rules indexed by a certain level. L, so that the set of nodes of the quadrature rule of level L plus 1 contains the nodes of level L. And so you hopefully see already that this is why we use levels and not numbers of points, because typically going from one to the next level means that I would almost double the points, refining the trapezoidal rule, for example. So before we come to the examples, why am I doing this? We can then define, if this is a given, the difference between two consecutive levels So I'm going to call this delta L, upper index for one dimension, G, and this is just the Lth one-dimensional rule minus the L minus first one-dimensional rule applied to G. We do this for all L, starting at 1, 2, 3, and so on. And we define that delta 0, well, no, I'm going to define this for Q, 0, 1 of G is just 0. Yeah, so we can start this definition with the differences. And then why is this advantageous, or what are we going to do with this? We can write a quadrature rule as a telescoping sum. A quadrature rule as a telescoping sum. And it's this QL1 of G. I can write now as Q01, which is 0 plus Q1, 1 minus Q0, 1 plus and so on. QL1 minus QL minus 1, 1. All of this applied to G, which means I can write this as sum I running from 1 to L of delta I1 G. And this doesn't seem so interesting for now, but that's actually the key to what we're going to do later. And why do we need nested quadrature rules? Because the difference kind of only makes sense then, because it then looks like a quadrature rule. It uses the same set of points on level well, it reuses the points of level L minus 1 on level L, so I'm not gaining additional points, and it looks like a quadrature rule on level L. So we note, so it's a linear combination of function values. So delta L1 G looks like a quadrature rule in which the nodes are the same as for QL1, and the weights are differences between the levels. Okay, so that's the thing that we can do now. I owe you some examples, and one example of a nested quadrature rule is the trapezoidal rule, or how I can construct such a nested quadrature rule. So the trapezoidal rule looks like this. So I'm on the interval 0, 1. So let's put this just here. When I'm at level 1, so here are the levels, I can use the leftmost point and the rightmost point. Yeah, so that's what the trapezoidal rule would do. So let's draw some lines here. Then if I refine, if I take the composite trapezoidal rule, I would take the point in the middle, and then at level 3 I could use those points, the point in the middle, and then refine every interval. Yeah, so again, that's why I'm using levels and not number of points, because roughly the number of points on the next level doubles. Yeah, so I'm going from 2 to 3 to 5. And then we can look at the weights that we would have. Let me add them here in red. So that's 1/2, 1/2. And then on the next level, it would be 1/4, 1/2, 1/4. So I can write down what the difference between levels 2 and 1 would be. So delta 2 in one dimension, G, is then 1/4 G of 0 with a minus sign. Yeah, so I have the 1/4 here minus the 1/2 plus 1/2 G of 1/2, and then minus 1/4 G of 1. Yeah, so that's this one here, which doesn't have a counterpart here, and then this minus this again. Yeah, so this is how it looks like. Formally, it looks like a quadrature rule, which uses the points of level 2. And then there's a more interesting example, the so-called Clenshaw-Curtis and Thayer rules, which I hope I'm pronouncing correctly. And Thayer. And I'm going to write them down for you. So the Clenshaw-Curtis notes are these. So ZLR, it's 1/2 1 minus cosine pi r minus 1 divided by RL minus 1, and R runs from 1 up to RL. Again, RL is the number of points on the level L, and the number of points is this. R1 is 1, and RL is 2 to the power L minus 1 plus 1 for L bigger than 1. Yeah, so similar to the composite trapezoidal rule, the number of points roughly doubles. And these nodes are the extrema of the Chebyshev polynomials. So these nodes, extrema of the Chebyshev polynomials and let me recall for you how they look like. Tn of x looks strange, but these are actually polynomials that I can define, and they map 0, 1, actually minus 1, 1, sorry, to 0, 1, yeah? So the Clancho-Curtis nodes by definition are defined on the interval minus 1, 1. And we will investigate the Clancho-Curtis rule later. They are the nested version of Gauss quadrature. Gauss quadrature, you probably remember from your numerics 1 class. One of the big disadvantages is that these rules are not nested. So if I refine, I need to compute everything new. Clancho-Curtis related to orthogonal polynomials. This time it's the extrema, and one figures out that the extrema nested. I'm not going to prove that they are nested, but you can do the math yourself. So if I look at these nodes roughly how they look like on the interval 0, 1, similar to Gauss points, they accumulate at the boundary. So in level 1, I again have both points on the side. Then level 2 is also easy. The point in the middle comes into play, and at level 3 it starts to be a little bit different. From the composite trapezoidal rule, the point is not in the middle anymore, but close to the boundary point. At level 4, I have this, and I fill closer to the boundary. Yeah? So this is roughly how the Clancho-Curtis rules look like. And the Thayer rules, or Fager, or however you pronounce it, rule uses the nodes of Clancho-Curtis. But without the boundary points. All right, so these are nested quadrature rules.